The topic of this talk is the wonders of electricity and magnetism. And so that raises the question, what is electricity and what is magnetism? And that's an easy question to ask, but of course impossible to answer in one lecture. There's so much to learn about electricity and magnetism. All freshmen who come to MIT must take a course in electricity and magnetism. And the physicists, the physics major and electrical engineering majors take courses about electricity and magnetism all the way through senior year and throughout graduate school. Now, some of you may already know something about electricity and magnetism, and that may even include Rose, who is 5 years old, but I'm not sure. You probably know that electricity can be dangerous. Lightning is a form of electricity, and lightning can kill you. You also know, or you should know, that you have to be very careful with electricity at home. In other words, you never stick anything in the outlets at home, and you never open any electric appliances. That can be very dangerous. You also know about magnets. I'm sure that most of you have magnets on their refrigerator. And you probably know about compasses, which are used for navigation, and they work only because of magnetism. I always carry a compass on me, always, wherever I go, a whistle and a compass. Where's the compass? Hard to find the compass. There it is. And that's not just for when you go hiking, but I use this very often in cities. It's very easy to orient yourself with a compass. And not only in New York, but I also use it here in Cambridge and in Boston. It's a wonderful thing to have. So I think we all agree that without electricity, we'd be in deep trouble. Remember Hurricane Katrina. No lights, no television, no radio, no computers, no refrigerators, no air conditioning, not even tap water. Because tap water requires electric pumps. I have a gas stove at home. Won't work without electricity because the ignition is electric. I have gas heat at home. Won't work without electricity because there is a fan in there to push the air out, and that fan is an electric fan. Now, in the absence of any form of electricity, there would be no cars, no airplanes, no trains, no cell phones, and you couldn't even walk without electricity because your muscles wouldn't work. Your heart cannot beat without electricity. I go even one step further. You couldn't even think without electricity. Now, I realize that there are people who cannot think even with electricity. But they are not in my audience today. In short, life cannot exist without electricity. Now, can life exist without magnetism? In other words, could we do away with those nice magnets on our refrigerator? Can we do without compasses? Well, of course we could. Yeah, we can do without all those goodies, but life itself cannot exist without magnetism. Magnetism and electricity are inseparable. One cannot exist without the other. And this was one of the great discoveries made in the 19th century. And I will say more about this later, of course, and I will also demonstrate that. So let's go back in time, and let's start with electricity. Some 2,500 years ago, the Greeks discovered that if you rub amber, that you can attract dry leaves, pieces of dry leaves. Amber is hardened resin, resin from pine trees, so it is petrified resin. And the Greek word for amber is electron, so that's where the name electricity comes from. In the 16th century, it was already known that glass and sulfur had very similar properties. And when you comb your hair, as I will show you later, thereby rubbing the comb with your hair, you may also be able to pick up dry leaves and small pieces of dry paper. In the 18th century, it was discovered that there are two types of electricity. If you rub amber, that is one kind. And if you rub a glass rod, that is another kind. Physicists talk about negative and positive electricity. Negative and positive charges. When you rub amber, the amber becomes negatively charged. If you rub glass, it becomes positively charged. A negative charge repels negative charge. A positive electric charge repels positive charge. But negative electric charge attracts a positive electric charge. It was Benjamin Franklin who suggested that all substances have a certain amount of what he called electric fluid. And if an object has an excess of this fluid, it's positively charged. If it has a deficiency of the fluid, then it is negatively charged. And his idea was that if somehow you transfer this electric fluid from one object to another, that one object becomes positive and the other becomes negative. And this was a brilliant concept, which in modern physics is known as the conservation of electric charge. What this is saying is, you cannot create negative charge without at the same time creating positive charge. I have here a helium balloon. And I'm going to rub a glass rod, make it positive. I'm going to put positive charge on this balloon. And then I will rub the glass rod again, and I will show you that positive charge repels positive charge. But before I do that, I have to admit something. And what I have to admit is that I should never ever have accepted to give this lecture in September. When Beryl called me 8, 6, 9, 10 months ago, and she said, would you want to give a lecture again for the museum? I said, of course. What dates are open? And she says, September 25 is open. I said, that's fine. I was an idiot. I have lectured electricity and magnetism for decades at MIT. And I know, I should know, that the demonstrations that we like to do require very dry air. No humidity, because the humidity makes the charge leak off the object. February, that's the time when you should give this talk. But now is not the time. And I'll admit something else to you. I've had sleepless nights for the past week. Absolutely sleepless nights. Following the weather, hour by hour. If it had rained this morning, and if you had walked in here with wet clothes, it would have been all over. If you think it is a little chilly here, 67 degrees Fahrenheit, why do you think that is? I have asked for the air conditioning to be on for 48 hours in a row, because an air conditioning takes the water out of the air, and I can't have humidity. So sorry that you pay the price for a low temperature. So now we will do this demo. We have to do it fast. In February I can do it very slowly. Today I have to do it very fast, because if I put positive charge on here, if I wait 1 minute, it will have leaked off. So we're going to rub the glass with silk. And then the glass will become positively charged. That's the way we define positive charge. I will try to put positive charge on this balloon. I'll try to put as much on as I can. I'll put a little bit more on. Okay. Now it should be having some charge, some positive charge. Let it calm down a little. And now I have here this rod, which is positively charged. Positive charge expels positive charge. Very convincing. But if now I'm fast, while the charge is still on there, if I take rubber, which becomes negatively charged, and I rub rubber, we rub it always with a cat fur. So if I rub this with cat fur, I should be able to attract that balloon, because that balloon is positive, and now the rubber is negative. Let's see whether that works. And there it comes. So you see now, you have seen positive charge, you have seen negative charge. You have seen that positive charge repels positive charge. You've seen that positive charge attracts. negative charge. Now, the idea of conservation of charge. That means if I rub this glass rod, and if the glass rod becomes positive, it means that this must become negative. Remember, Benjamin Franklin idea. Put electric fluid on here is positive, this becomes negative. So let's see whether I can prove that to you. By now, a lot of charge may already have leaked off because it's September. But I'll put a little bit more on it. A little bit more positive on it. And then I'll try to make this rod again negative, very positive, the rod very positive. And so the silk now should become negative. Conservation of charge. And you see? It attracts it. You see that? So now you've seen that if the rod becomes positive, that indeed the silk becomes negative. If I comb my hair, then I really could not predict whether the comb becomes positive or negative. But we can bring that to a test. Because we know now that the balloon is positively charged. And so if I comb my hair, if the comb became positively charged, it would repel the balloon. But if my comb is negatively charged, it would attract the balloon. Hey, it attracts the balloon, so my comb is negative. Now you may think that this business of positive and negative charges, this idea of repelling and attraction, you may think that that is very similar to magnets, since magnets can also repel each other and they can attract each other. But that is a complete misconception. There is a very fundamental difference between plus and minus electric charges on the one hand and the poles of magnets, which we call north and which we call south pole. Here I show you a bar magnet, and we have one here, we have actually two here. Here's one, and I have another one here. And this side is red, and this happens to be what we call the north pole of the magnet, and this is the south pole. I have another one, also colored, color-coded. So this side is the north pole, and this side is the south pole. Now, the north pole attracts the south pole. I can easily show that. This is the north pole, this is the south pole, and they attract each other. So this south pole attracts this north pole. However, if I rotate them, the north poles will repel each other, and the south poles will repel each other. Look at it. North pole, won't work. They repel each other. South pole, doesn't work, repels each other. Suppose now I take a piece of plastic, which I can do, and I put negative charge on the plastic on one side, and I put positive charge on the plastic on the other side. I can do that. I can have another piece of plastic whereby the positive charge is also here and negative there. Now, positive will attract negative. But clearly, if I rotate them around, negative will repel negative, positive will repel positive. So now you think there is an enormous parallel between magnetism and electric charges. And that is a misconception. Because if I take a saw and I cut this in the middle, the left side of that piece of plastic is only positively charged. So here it is. And the right side is only negatively charged. But now I take an axe and I cut the magnet in the middle. And what do we have now? You think I have a south pole on the left side and a north part on the right side? The answer is no. You end up with two magnets which each have a north pole and a south pole, and this part also has a north pole and a south pole. So there is no such thing as cutting a magnet and then having one piece which is only a south pole and one piece which is only a north pole. So you always have with a magnet, no matter how often you break it, you always have two poles. We call those dipoles in physics. Di stands for two. A dialogue is a discussion between two people. If you could make one piece of magnetic material only a south pole, we would call that a monopole. Mono stands for one. A monologue is one person talking like now. So yes, electric monopoles exist. A positive charge is a monopole. Electric positive charge is a monopole. A negative electric charge is a monopole, but magnetic monopoles do not exist. Someone in my audience may find a magnetic monopole in the future. And if you do, you will definitely get the Nobel Prize for Physics. And physicists have tried for decades, and still trying today, because from a theoretical point of view, there is no reason why they shouldn't exist, except we have never seen one. So here is a task for you. Now, electric charges are exceedingly small, and they can move. You've seen it. I could move them from the positively charged rod. I could bring them onto the balloon. Now, the negative charges, which have a name, we call those electrons, are much smaller and they are much lighter than the positive charges. And so the negative charges can therefore move much easier than the positive charges. And when electric charges move, it's almost always the electrons that move. And when that happens, when electric charges move, we give that a name, we call that an electric current. Electrons can very easily move in metals. Copper, iron, aluminum, silver, gold. Metals conduct electricity very well. If you take porcelain, take glass, plastic, rubber, or uncooked spaghetti, doesn't conduct electricity very well. We call those insulators. Porcelain is a very good insulator. So the electric wiring in your house is made of copper because it is such a good conductor. Dry air is a very decent insulator. Humid air is a lousy insulator. And that's why we have problems in September and not in February. It is not dangerous to touch at home your electric cords. The reason is that the outside is properly protected with an insulator. But if you cut the wire and you strip off the ends, then you see here the copper. So that is really where the electric currents occur. But there's no danger because it's properly protected. Now this piece right now is potentially very dangerous. And when we have going to be a 10-minute break, you can be sure I will remove this piece. And why do you think I will remove this piece? Because some of you might just plug it in, and then, what do you think? If someone touches that, that is very dangerous. So we're going to remove that, but you have at least seen the idea of an insulating on the outside and conducting copper on the inside. You see here a helium balloon filled with helium. Suppose we have this balloon here, and the balloon is not positively charged, and the balloon is not negatively charged. We call that neutral. There's no net charge on it. But I approach it with a glass rod, and the glass rod has been rubbed with silk, is positively charged. The balloon will come to the rod, even though it is neutral. Why does it do that? Well, electrons are being attracted by the positive charge, and they can move very easily. And so electrons will move to this side. Some electrons will move to this side of the balloon, but you can't create charge out of nothing, so the other side automatically becomes a little bit positive, because the whole thing is still neutral, no net charge on the balloon. So now you get a separation of charges in the balloon. The negative charge is attracted by the positive charge. The positive charge is repelled by the positive charge, but these are closer together than these are. And so the attractive force wins over the repelling force. And that is called induction. And I will demonstrate that to you. So before I demonstrate that, I must be sure that that balloon is completely neutral, that there is no charge on it anymore. In order to do that, I will have to touch it, I will have to kiss it, I will have to do all kinds of things to make sure that whatever charge is on it has been removed. Otherwise, it's not a fair experiment. Okay. So now we take the glass rod and we have the silk. And all I want to show you now that if I approach this neutral balloon, there's no positive charge on it. When it sees the positive glass rod, it will come to the glass rod. There it is. That's induction. It's still neutral. There's still no charge on it, but that's induction. Put them in here to keep them dry. You may now understand why rubbed amber, which the Greek already knew a long time ago, attracts dry pieces of leaves. That's induction. And you may also understand that if you comb your hair and the comb gets charged, that you can now also pick up small pieces of paper, because that's induction. Even though those pieces are neutral, this phenomenon will make the paper go to the comb. And I want to demonstrate that. But given the fact that the humidity is very high in this room, I prefer to make sure that my hair is very dry so that I get a maximum amount of charge on that comb. So even though I washed my hair this morning, without that, it would never have worked. You must wash your hair if you do any of these experiments first. But I also want to dry my hair because that is important. So let's do that. In February, I don't have to do this, but it's September. Let's hope that that is enough. I have small pieces of paper here. It's confetti. I'm going to put them here, and you're going to see them projected there with a small television camera. And then I will comb my hair, and I will show you whether I can attract those small pieces of paper. So let's first television on, and let me check my notes to make sure that we have the proper lighting. All lights off, and spots 1, 2, and 4 off. So there you see the confetti. Now I'm going to comb my hair. There we go. You see that? Some of the confetti comes to me, to the comb. You see it? But now, hey, there's something very special. Some of that confetti comes to the comb and immediately leaves. Why do you think that is? Why do you think that happened? So the paper came up, I will show you again, and immediately the pieces of paper would be repelled by the comb. You see them go down again to the table, some of them? Why is that? Come on, don't be afraid. In the worst case, it's wrong. I think you mean, well, when the paper touches the comb was negative, remember? We had already decided that earlier. The pieces of paper take some negative charge because they touch the comb. Now they're both negative, and so they repel each other. That's fine. But now there is another problem. Some pieces of paper get stuck on the comb. I can show that to you again. You see that? They're stuck. And I will leave you with that question. Why is that? I always leave my students with a problem that they have to digest at home. You can discuss it with your parents, you can discuss it with friends. Why is it that some immediately repel, but others permanently, for a long time, stay on the comb? The whole process, of course, is induction. That's clear. Why do some stick? I have a nice collection of balloons. Oh, I popped already too. If I rub these balloons, it shouldn't surprise you that the balloon gets charged. We've seen examples of that. That's induction. Why does it stay there? The same problem with the paper and the comb. Why does it do that? Why does it not immediately after it touches the board, why doesn't it immediately repel? It's stuck there. Stuck there. Stuck there. That's interesting, isn't it? I can see that Rose would very much also like a balloon on her. And I would color very well with your shirt. Why don't you stand up, Rose? And I will put a nice balloon on you. No, just like that. Just stand here. Come here. Yeah. Look at all these people. Yeah. Wonderful. I want to sit down. Careful. Oh boy, I forgot this one. This is a real biggie. That's a nice one. If I rub this one, will it stick to the... Do you think it will stick to the blackboard? Who says it will stick to the blackboard? Come on. Ah, Professor Marvel Valle. What did you say, Nurtjes? It will stick? And Professor Hudson, what will he say? Will it stick? He says no. And Professor Bertschinger? It will stay. Who says it will not stay on the blackboard? Okay. Why is that? Why doesn't this one stay and the others do? Yeah? It's too heavy. That's right. It is so much heavier than the others that they have no problems, but this one does. That's all it is. It wants to stick, but it's too heavy. So I'm very careful. Put the blackboard a little lower, maybe. So you see, those who said it would stick were right, and those who said it's not going to stick were also right. Obviously, no professor at MIT could make that mistake, so that's why they were all three right. I now want to explore further the idea of conservation of charge. And what I want to do is I want to charge up a student by beating the student with cat fur. And then the student will get a particular charge, plus or minus, whatever that is, and I, who am the beater, will get the opposite charge. And then we will see whether we can demonstrate to you that when we touch each other, that indeed the charge from him or from her goes to me. I need a volunteer for that, someone who is very brave. I want really a youngster. I know you've been a student of me for many years, but I want a youngster. And you're so close. What is your name?
Alex.
What?
Alex.
Alex. Alex, are you a little nervous?
No.
You should be. Now you see, this is cotton, right?
Yeah.
Not
Yes.
good, not good. Don't take it off, but we need something more synthetic. And this is what you're going to wear. Okay. Now, we're going to put you on a stool which is very well insulated, so that the charge cannot easily... No. We don't want any accidents, just sit there. Okay, now make sure that your feet are always on this plate, because we need very good insulators, not on the wood. Yeah? Okay. Eric was your name? Alex. Alex is going to hold this in his hand, which are tinsels. You're going to hold it high up. And when Alex gets charged, you will see that the tinsels also get charged. You should hold the tinsels themselves in your hand, the metal, yes. And so the tinsels will get charged, but equal charges repel each other. And so you will see that the tinsels will start doing this. And so that will tell you then that Alex is going to get charged. And I will also have tinsels in my hand, and so you will see that I also get charged. You will not be able to tell that his charge is the opposite charge of me, because that's the conservation of charge. Then I will touch Alex, and we'll see whether there's any reason to believe that, indeed, there is charge moving between us. That means an electric current. Are you ready for this, Alex? Are you still not nervous yet? Okay, man, I got to get a nice piece of cat fur. This is a good one. And I will join you. It's funny, you're not nervous, but I am. Man, this is dangerous stuff. Oh. Okay, so hold it like that. You ready? There we go. See the Tinsels? Oh, I should have had mine. Where are mine?
Yeah, where are yours?
I'll get mine. I'll get mine. Just stay where you are, right? Okay, you see, I'm also charged. He is charged. Look at me, look at me, look at me, look at me, look at me. I want to see your nose. I wanted to touch your nose. We have to do this again. We have to do it again. Okay, ready? Okay, turn to me. Stay where you are. Stay where you are. Alex, we're going to make it worse now. Give me the tinsels. Alex.
Oh, yay, I love this stuff.
I have here
A cap for what?
a neon flash tube.
Okay, and I hold the 10 lights. Or you hold one end and I hold that.
You've seen this before.
No, but I can guess.
Okay. Now I want you to hold this in your hand. And under no circumstances, no matter what happens, let it go. Because it will break and they're very expensive. So you're going to hold this in your hand. And now I'm going to beat you again. And instead of touching your nose, I will now hold it, I will touch the other side. And if now a current is flowing strong enough between him and me, you may see some light. And that tells you then that indeed,
Why don't we just turn this thing?
that comes later, Alex. Yeah. That comes later. You're a little impatient. You are a perfect MIT student. So Alex, hold that in your hand, and I'm not joking when I say don't drop that. I have to set the light in a very special way so that we have optimum. I'm going to turn all off. Make sure I have the... Marcos, maybe you could help that I will beat him first, and then at the very last minute, before we do the discharge through the neon tube, that you then turn all the lights off. Yeah. All off. I already have the spotlights off. Oh. So all you have to do is all off, okay? There will still be a little bit of light from the side, but there will be very little. Okay, Alex, so just hold it up like this in front of it so that I... No, here, so that I can... No, point it to me, because I should be able... Yeah, okay. You ready? There we go again. Okay, Marcos? Once more. Hold it. No, Marcos. Yeah, you can leave it off. There it is. You are a hero, Alex. Now make sure that you get off safely. Good for you. Thank you. So where is this tool? Let's remove this because it blocks the vision. So a nice example of the conservation of electric charge and also of the charging up. Now let's go back in history and talk a little bit about magnetism. Our ancestors had known about magnetism for at least 2,500 years. The Greek knew that some rocks attract bits of iron, and these rocks were very common in the district of Magnesia, which is now western Turkey, and so that's where the name magnetism comes from. And about 1,000 years ago, already the Chinese made compasses using this material that was found. It is called magnetite. So they already made compasses 1,000 years ago. And in the 16th century, it was discovered by Gilbert that the Earth itself is a giant magnet. And then, if I make a big jump, a major breakthrough came in 1819, 1820, was made by the Danish physicist Ørsted. I referred to that earlier. He discovered that a compass responds to an electric current going through a wire. And that established the link between magnetism and electricity. And this magnificent discovery caused an explosion of research in the 19th century, and it led to our understanding of why and how electricity and magnetism are inseparable. Needless to say that this led to a technological revolution which still continues today. Think about your cell phones, think about your computers, your computer games, and even your iPods. It gives us a certain quality of life that we are used to. We take it for granted, but of course many people on Earth are not as fortunate as we are. And I want to do now the demonstration that was that breakthrough. I will show it to you there, but first you can see it from where you are sitting. We have here a 12-volt car battery. I will talk about batteries later more. A battery is an instrument that can push charges. A water pump can push water. Batteries can push charges. So for now, take my word for it that that battery can make a current go through the wire which we have here. And here I have a compass. And this compass we put on top of this wire. And the compass right now is pointing roughly to the north. But then, when I make a current go through the wire, you will see that the compass changes its direction. And that was the big breakthrough made by Ørsted. So, let us get the right setting for that. It's probably number 2. Yes, it is. Now we get the right light settings. So we get all off, and we get 1 off. So you see the compass needle in this direction, and you see the wire which is in this direction. So now I'm going to connect this battery with the wire, and I'm going to have a current going through. I will tell you, I don't even have to tell you when the current goes through. You will immediately tell. Now the current, I break the current, and the compass goes back to its original direction. Now I let current go through, and there you see that the magnet indeed responds to the current. And so we must conclude that the surroundings of this wire, when a current was going through it, became magnetic. A physicist would say the current creates a magnetic field. We like to use that word field. We have electric fields and we have magnetic fields. In other words, moving electric charges, that means a current, creates a magnetic field. That is what Ørsted showed. Now comes a key question. And it is so important, this question, that I will ask you the question twice. If moving charges, that means electric currents, can create a magnetic field, can a moving magnet create an electric current? I will repeat that question. If moving charges, that means an electric current, can create a magnetic field, can a moving magnet create an electric current? And the answer was given by Michael Faraday in 1831. And the answer is yes, it can do that. And obviously, I'm going to demonstrate that to you. The way I will demonstrate this to you is as follows. I have a coil, thousands of windings. I really don't even know how many. There's probably thousands. It's here. So here is one end of the coil, and then you have thousands of windings, copper wire. They don't make contact with each other. They are varnished, so there's insulation between them. They go around and around and around and around, and then it comes out here. That's the end of the coil. And I put a light bulb between those two ends. So this is my symbol for a light bulb. And I'm going to move this coil through this magnetic field. This is a very strong magnet. And when I do that, you will see a little bit of light. And the faster I move, the more light you will see. The magnet that we have is very heavy. Therefore, instead of moving the magnet to the coil, I will move the coil to the magnet. That shouldn't make any difference, but it is a lot easier for me. So let's show it to you there, so that we get the best possible image. Yeah, so all off. And then we have 1, 2, and 4 off. Ah, yeah, Marco, sorry that I should have waited for you. Yeah, so I'll get you number 1 again, right? Yeah. Number 1. So you see here the magnet. Go a little, show me a little higher. Yeah, that's fine. So this is the opening of the magnet. It's a very strong magnet. And here comes the coil, and I'm going to move the coil. And as long as I move it, you will see a little bit of light. When I stop moving it, light goes out. Watch it. Can you see it? You see light as long as when I move. And the faster I move, the brighter the light. If I move very fast, and I can't promise that, but it's possible if I move it very fast that this light bulb goes to pieces. Who would want to see that? You're just like all my MIT students. Destructive characters. Who does not want to see it? The saints. We have the saints and we have destructive characters. Okay, let's try it. I can't promise you. Is it broken? Yes. It's no longer working. So I lifted it out very fast, and it broke already. So you see, speed is very important. When Faraday made this discovery, he was asked by a news reporter whether this would ever be of any practical use. And he answered, "Someday you will tax it." He had that vision. Now, indeed, what you have seen here looked in the 19th century as a very innocent demonstration. However, this simple phenomenon, and what I'm going to tell you now is no exaggeration, this simple phenomenon runs our entire economy. It runs our entire economy. Without this phenomenon, we would still live more or less like our ancestors in the 17th and 18th century. We would have candle lights for light. No radio, no television, no telephones, no computer, no internets, no laptops. Stone Age. Imagine how miserable your life would be without TV, without computer games, without video games, without your iPods. Why don't you admit it? You spend a lot of time, right, in front of the tube. Your life would be very miserable. So electricity is produced by electric generators, by power stations, we call them. And all they do is they move copper coils through magnetic fields. Now, if you want to move a copper coil through a magnet, you have to do work. That means you have to put in energy. I put in the energy when I moved it in and out. But if you want to do that on a big scale, you need energy sources to do that for you. You need, for instance, coal, which is a very common source of energy, or oil, or nuclear energy. They drive turbines, and those turbines rotate coils through magnetic fields. Now, of course, you can also generate electricity with waterfalls, like the Niagara Falls, and in some cases with wind. But it takes energy to produce electricity. Light bulbs and all kinds of electric appliances consume energy. And this energy consumption is expressed in terms of watts, named after James Watts, who did a lot of research in this area in the 18th and 19th century. You have light bulbs at home who are marked 40W, that means 40 watts. And you have others at home that may say 100 watts. They produce more light. It means that this one, if you run it for 1 hour, uses 2.5 times more energy than this one. So this is the energy consumption. I have here an electric generator. You can rotate this crank, and then you can power this light bulb. It's a 20-watt light bulb. And that takes energy. So someone has to come, some volunteer, who's willing to do that. Now, Ed, would your son be willing to do that? Don't feel obligated. There are plenty of volunteers. So what is your name?
Thomas.
What?
Thomas.
Thomas. Are you strong?
Yeah.
Ah, that's exactly what we need, man, a strong man here. Now, why don't you start rotating, and then let's see what happens with this light bulb.
Does it matter which way?
No, it doesn't matter which way. Just rotate whichever way is comfortable for you. Fantastic. Hold it, hold it. I will change the light situation a little bit so that we can see it even better. So I'll put you a little bit in the darkness, but not much. Go ahead. $20 watts. Keep going, man. Keep going. Are you getting tired? No. Hold it, hold it. I can see that this is too easy for you. Way too easy. You see what I can do? I can make a small change in this circuit, and now I can ask you to power 1, 2, 3, 4, 5, 6, 6 light bulbs of 20 watts. That is 120 watts. Go ahead. Thomas, 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 you're letting me down, man. I see hardly any light. Keep trying, come on. Getting tired? Man, you said you were strong. If you, at home, have a 120 watt light bulb, and this is equivalent to 120 watts, and you have that on for 10 hours, the electric company will charge you 10 cents. Thomas, you think you can do that for 10 cents for 10 hours? Try it. Now, Thomas, I think we can both agree that the bill from the electric company is a bargain, right? It's a real bargain. Thank you, Thomas, you did well. I do a lot of hiking, and I always have an emergency pack with me, just in case something happens. And one of the things that you always have with you when you're in the mountains is a flashlight. In case of an emergency, you can't make it home in the evening and you have to stay and it gets dark. But we all know that when you need that one flashlight that has been in your backpack already for 6 months, that the batteries are gone. And so therefore, experienced hikers have a generator like that. I have this one. Where's Thomas? Thomas, what do you think? 300 watts? 500 watts? I can do this for 10 hours. You think this is 300 watts? Maybe, Thomas, I doubt it very much. This may only be 5 watts. But that's the idea. This is an electric generator. And so I'm rotating coils through magnets. And that is the same idea as what I showed you here. And it's the same idea what Thomas tried. And that was very, very difficult. 120 watts is very, very difficult indeed. I suggest now that we have a 10-minute break, and I invite all of you to come here and play with all this stuff as much as you like. Try not to break it, but we can look at Ørsted again. We can do the comb experiment again. You don't need the television. Whatever you want to do is fine with me. You can also use this, this coil. We will put in a new light bulb because we broke this light bulb. And then 10 minutes from now, we will reconvene. So take a rest for 10 minutes. All right, well, you enjoyed yourself. Thanks for that. And you didn't break too much. Radios, light bulbs, toasters, vacuum cleaners, refrigerators, air conditioners, electric clocks, vacuum cleaners, telephones, electric toothbrushes, all need a source of electricity. And so what sources of electricity are there available? Well, there are these power stations, electric generators, of which you saw one there. And they bring in your home 110 volts. Just stick it in the wall, so to speak. And then there are batteries. And as I said earlier, a water pump can move water, and batteries can move electric charges, so they can produce an electric current. Now, some pumps are more powerful than other pumps. And therefore, batteries come in a huge variety. Very common are the 1.5 volt batteries, 9 volt batteries, and the 12 volt batteries, the car batteries. This is one of them. We removed the Ørsted so that you can see the 12 volt battery. It's a typical car battery. The size of a battery does not tell you its voltage. A 1.5 volt battery, which is used in watches, or in hearing aids, which I have, like teeny weeny. And the 1.5 volt batteries in flashlights and radios are substantially larger. Volt is named after an Italian, Count Alessandro Volta, who did a lot of research in the 18th and 19th century. Now, to operate properly, electric appliances require a specific voltage and a specific electric current. And if the voltage is too low, either they don't work properly or they don't work at all. And if the voltage is too high, then you can blow them to pieces. If a radio is designed to work with a 9 volt battery, it won't do anything for you with a 1.5 volt battery. And if you ran that radio at 110 volts, it would just blow up. Now, what determines the amount of current going through a light bulb or a radio or a coffee machine or any appliance for that matter? Well, it's determined by the voltage, and it is determined by what we physicists call the resistance of that appliance. Suppose I have here a battery, just schematically. Let's say this is plus and this is minus. And suppose I connected that with a copper wire. This is copper now. Copper is a very good conductor. That means it has a very low resistance. So a huge current will run, and the battery won't last very long. Now, I connect this with uncooked spaghetti. Pretty good insulator. Very high resistance. Not very current will run. So the battery will last almost forever. So the higher the resistance, the lower the current. And so the word resistant is a very good word, because it is the ability of the appliance, if you like to think of it, to resist current for a given voltage. Now, what I'm going to do now may be too tough on some of you. It's certainly going to be too tough on Rose. But maybe not on all of you. I'm going to write down one and only one equation. And some of you may have seen that equation in school. But if you haven't, that's okay. Then just forget about it. And that one equation is the following. V, which stands for voltage, equals I, which stands for current. Now, why on earth we physicists have chosen the capital letter I for current, it beats me. Maybe Professor Bertschinger knows it. I don't know. Maybe Professor Hudson knows it. I have no idea. Nurtjes, do you know? We use I for current. V equals I, that is the current, multiplied by R, which stands for resistance. That makes sense. This is a very famous law, and this is called Ohm's law. So suppose you have a 9-volt battery, and you run two different appliances. Then you have 9 equals I times R. But one of those appliances has a very low resistance. Well, then the current will be high. Another appliance has a very high resistance. Well, then the current will be low, because I times R in that case is always 9. So the appliance with the highest resistance has the lowest current, and the one with the lowest resistance will then have the highest current. I have there a 100-watt light bulb. And this light bulb is designed to run at home in the outlet 110 volts. And so I can turn on this light bulb for you, and you see 100-watt light bulb. Nothing exciting. It is designed for 110 volts. If now I lower the voltage, and we can do that, we have an instrument here to lower the voltage, then what happens is, so you have for this light bulb, you have 110 equals I times R of this light bulb, and I call it light bulb number 1 because later I have another light bulb for you. And so, don't you like this? Oh, thank you very much. I was too thinking of light bulb thinking. Oh, thank you. You passed the course. Who was that? Who? Okay. Oh, no, you didn't pass the course. All right. So now you see, when I lower the 110, the resistance of the light bulb stays approximately the same, and so the current will go down, and you see less light. That's an application of Ohm's law. So I lower now the voltage, take my word for it how I can do that, and the light dims. I have light dimmers at home, so there is actually an application for this, a useful application. The idea being, though, that if you run it at a lower voltage than it's designed for, well, then it doesn't work so well, or in some cases, it doesn't work at all. I have here an electric fan, which I'm sure many of you have at home, and this is designed to work at 110 volts. You can turn it on. There it goes, and it's happy. It sees it's 110 volts, and see, works wonderful. Works very well. Thomas, you may even feel the wind, don't you? You feel the wind? Now I'm going to lower the voltage, so the resistance remains roughly the same, and so it's not going to work so well anymore. Much lower speed. Very clear. So when you run something at a lower voltage than what it was designed for, it doesn't work as well, or it doesn't work at all. I told you earlier, take a radio, it's a 9-volt battery, you put a 1.5-volt battery in and it won't work at all. What may some of you, who are those of you who are thinking destructively, what some of you may find more interesting is not to give something a lower voltage than it wants, but to give it a much higher voltage than it wants. Because now, when you do that, you break things. And to accommodate you, of course, I thought of that. Let's make it a little dim. I have here a light bulb, which is designed to run on a 12-volt car battery. And the car battery is connected to this wire. Okay. And so I can run that on a 12-volt car battery. Run the spots off. Okay, so ready for this? That's it. Aren't you excited? You came all the way to see a 12-volt light bulb being powered by a 12-volt battery. But we can also power it with 110 volts. Is this a stupid thing to do? Yes. Should we do it? No. Are we going to do it? Yes. That's what happens. So this light bulb was designed for 12 volts. It lived happily after, but what do? We run it at 110 volts. And then, of course, the filament current is huge. It is designed to run on 12 volts. So I'm going to write down again Ohm's law for you. So this was 12 equals I times R of the second light bulb 2. And now, all of a sudden, I make this 110. The resistance of the light bulb doesn't change by very much, and so a 9 times higher current through the filament makes the filament too hot, and it explodes. End of the light bulb. When I stick my fingers in the electric outlet at home, one finger in the left and one finger in the right, I can kill myself. And the reason is that 110 volts, the resistance of Walter Lewin is too low, I get a high current, and that's the end of Walter Lewin. And you should never, ever do that. However, if I touched the 2 poles of a 12-volt car battery, probably nothing happens. Let me try that. I was just kidding you. There's nothing that happens. Why? Because once you lower the 110 to 12 volts, Walter Lewin, the current going through me is much lower, and so I am happy. There is a way that I discovered already when I was a student that you can test these 9-volt batteries. Not by putting your fingers on it, but by putting them on your tongue. Because when you put them on your tongue, there will be a current going through your tongue, but your tongue is extremely sensitive. And you will know. If it hurts a lot, it's a good battery. If it hurts a little, not so good. And if you feel nothing, believe me, throw it out. No sense keeping it. I don't really know whether these are any good. I'll try this one. Yeah. This is a good one. This is not so good. Yeah, this is a good one. So that is an easy test, which sometimes comes in handy. So now comes the question, is a high voltage always dangerous? Namely, putting my hands, left finger and right finger, in the outlet is dangerous. Is it always dangerous, the high volt? Well, it often is. But I will show you today that I can generate easily 30,000 volts, touch it, and survive. If you comb your hair in the winter, maybe not today, but if you comb it in the winter and your hair is dry and nicely washed, then the difference between the comb and your hair could easily be 30,000 volts. And this voltage is so high that sparks can fly over between your hair and the comb. It's like spark plugs in a car. In a way, it's like lightning. So there is a current that will flow through the air between my hair and the comb. But there is so little electricity, so little electric charge on my hair and on the comb, that the current that will flow is not high enough and it doesn't last long enough to kill me. So it's completely innocent, even though it is 30,000 volts. But the 30,000 volt collapses to nothing the moment that a spark flies. Now, as you comb your hair, you may also hear some cracking. And in fact, when I was combing my hair early on with this experiment, I did hear some cracking, which made me feel good, because that means the air is reasonably dry. You may hear some cracking because these sparks that fly, that you may not have heard, make some sound. And in fact, if you do this in the winter, and I would advise you to do that, turn all the lights off in a room, make sure it's dark, go in front of a mirror, make sure you have washed your hair, that your hair is dry, and you comb your hair, and you actually see sparks. You hear them, and you can see them. Even better, which I have done countless times when I was a student, a freshman. What I would do is I would go in front of a mirror, and I would wear a nylon shirt. You really should wear a nylon shirt and not cotton. And then in front of the mirror, when everything is dark, you take the shirt off very slowly. And then you see a zillion small sparks, and your shirt is glowing like a light bulb. It's really a fantastic experience. So I recommend all of you to do that. Wait until February, and it's even more fun if you do it with a friend. You should do it together. Now, of course, needless to say, I was planning to do it today, but the humidity is too high, so it won't work. So you have to wait until the air is really very dry. And that's no joke. It makes a huge difference how long the charge can be kept. And the humidity is just, has too low is a very poor insulator, and so the charge just leaks off you. Perhaps you remember when you sit in your car and you move on the seat, or when you scuff your feet, and then you touch the doorknob, and you have a spark. You draw a spark. Does it kill you? No. Is it unpleasant? Yeah, it can be unpleasant. You may get a small shock. And the difference in voltage between you and the doorknob could easily be 30,000 volts. But the moment that you touch it, it collapses to nothing. Current is not high enough, doesn't last long enough, and so there is no danger for you. You will, just a little bit of a nuisance, but that's all there is. When I was beating Alex, there was easily 30,000 volts between him and me, probably more. But we're still alive, at least I am. How about you, Alex? It looks like he is also alive. Now, this phenomenon of sparks has a name. We call this electric breakdown. And so the higher the voltage and the sharper the objects are, the easier it is for these sparks to develop. And so hair is ideal, because hair has sticking out like needles. So it's ideal for electric breakdown. I have there in the corner a spectacular battery which runs only on water, and it can easily produce, in the winter, 60,000 volts. Today, maybe only 20,000 or 30,000 volts. And before I demonstrate this, I want you to understand how easy it is to build one, because it is an ideal project to do at home. What you see here at the top is a plastic bottle filled with water. And then you see some tubing coming down, both sides. You see that here. All nicely insulated, plastic. Just regular tap water, nothing special. And then here is a coffee can, and here is a coffee can. Open here, open here, open here, open there. Must be metal. Everything that you see here in red must be metal. That's essential for this to work. And now you let water run out here, and you let water run there. So you see water running here. You can sort of adjust it. And it be collected here in two metal buckets. Here is one of them, and here is the other. What is important now, that with some copper or some other wire, you connect this can with this one, and this can with this one. This means that these two should not touch each other. It means you have to jump over it. You see them here, They are not touching each other. And now you put on both these cans a metal rod, and then at the end of the rod, you can easily demonstrate that you get sparks, you can get 60,000 volts, and today, as I said, maybe only 20 or 30,000 volts. And this is called the Kelvin Water Dropper. It was invented by the Englishman William Thomson, Lord Kelvin, in the 19th century. So I will start it running now, and then I will change the light situation so that you have a better look at it. I think it's running. Yeah, if we have bubbles, that's not so good. Is it the TV setting 3?
Yes.
Yeah. So let me change the light settings a little. All off, and 1 and 4 off. So there you see the ends, the opening here, and if you wait and you look, you will see there is a spark. So look at you can see it either here, but also look there. Have to be a little patient, and there's another one. And so the gap opening is like a spark plug, is about 0.5 centimeter. So I would say 15, 20,000 volts easily. And this can be built at home. Now I'll tell you what is key if you want to build it at home. It's not difficult. But what is key is that this can and this can are supported by very high insulating material. You can see that here. This is a huge glass rod or plastic, and this is also plastic. Equally important is it that these buckets at the bottom, which are made of metal, are completely insulated from the table. So you can put them, for instance, on a stack of glass plates or porcelain plates if you have them. But if you put them straight on the table, it will never work. And that's the mistake that most students make, that they don't have the proper electric insulation where it's needed. Here, this has to be supported with insulators and also at the bottom. And then you can do it. It's not that difficult. The ultimate battery, the mother of all batteries, was invented by Robert van der Graaff. Robert van der Graaff was a professor at Princeton in 1929 when he designed what we now call a Van der Graaff generator, which generated, I think, something like 400,000 or 500,000 volts. And then he came to MIT in 1931. He was professor here, and he built here the Van der Graaff generator, which can generate 1.5 million volts. We have a super one here. It's not in the room. It generates 600,000 volts. We use it in February, but not in September. It's sick today, too high humidity. We have another one which is not bad. You see that here. And this one in the winter would easily generate 300,000, 400,000 volts. Today, more like 150,000 volts. A very respectable number, nevertheless. Now, could this machine kill me? Frankly speaking, I'm not sure. I have never tried. But of course, we can bring that to a test today. The first thing I want to do with this Van der Graaff is to see whether we can draw any sparks. There, we could only draw sparks over 0.5 centimeter. But here, since we have a much higher voltage, we can probably do much better. So I'm going to first run this machine, and then I'm going to turn off the lights, and then we'll see It's always nice. The spotlights don't want to go off. That is not unusual at MIT. Okay. Oh boy. Oh boy, you can. Oh look, it's fantastic. I don't have to do much myself. Oh, that's the tinsel. Alex, you left the tinsel there. Okay, now it stops. Let's see. So yes, you see we can draw sparks, and even though we could only draw them there over a distance of about ½ a centimeter, this is more like 4 or 5 inches, so it's substantially higher. So that's one thing you can do with the Van de Graaff. I wonder if I put some confetti on top of this, what do you think would happen? Ah, you're good, Alex. What do you think? Anyone thinks that it would get stuck maybe, like on the comb? Or would it all go boom? You think it will go boom. Who thinks it will also whoosh, immediately leave the dome? Raise your hand. And who thinks that it may actually, some of it may go off, but some may actually stick to it, just like in a mysterious way that the balloons did that? All right. Well, let's bring this to a test. That shouldn't be too hard. So we're going to put some on it. Whatever happens, it will go fast. Okay? You ready? It's already gone. Now do it once more. We understand that now, right? Because whatever the charge is on that dome, negative or positive, I don't know, whatever the charge is, of course, these pieces of paper get the same charge and they repel each other. So let's do it in a different way. I will slowly run up the Van de Graaff. There it goes. Now we're going to do a few experiments which are a little bit more dangerous. And for that, I hope that Marcos will assist me. If I stand on a stool and I make sure that the stool is very well insulated so that no current could flow through me, then if I touch the dome, my whole body will also become 150,000 volts. As long as there's no current flowing through me, there's no danger. And so I may be able to show to you that indeed my body then becomes, my whole body gets to 150 volts. And then these tinsels will then be spreading out, just like that happened when we did the earlier experiment. Can you turn this on? Here, there, you see it. You see this? You saw something else, did you? Let me turn it off. So if now I jump off, then you would expect that I discharge, right? Yeah, I would. Let's try that. Slowly. If I take my shoes off, it would go a little faster because my shoes have thick soles, and that means a lot of resistance. But you see, the charge leaks off me. Suppose I put some confetti on my hand. Would the confetti then go? Where is it? Here. Who thinks it would? Who thinks it would not? Who thinks it would stick on my hand? Okay. Are you ready, Marcos? Yeah. Yeah? Make sure that I first touch the dome, right? Yeah, go ahead. Now, as already mentioned by Alex, you notice that my hair was not normal. It never is, by the way. But today it was especially not normal because my hair was actually doing the same thing as the tinsels. It was going to stand out. But I have relatively short hair, so it would be nice if we have someone, maybe a volunteer, to do it. Oh, man. Oh, no. Oh, no. No, we need better than that. For instance, if we can find no one in the audience, then I can certainly put on a wig. And I will do that, and then surely I would be happy to have a volunteer. Yeah, you would, come on, your hair is too short. Your hair is dirty. It's clear that did you wash your hair this morning? Just be honest about it, otherwise it won't work. You're not sure whether you washed it. Why don't you come? Looks washed. Yeah. So why don't you first stand here? So what is your name? Rachel? Okay, Rachel, you stand there. Are you scared?
No.
This time you should be. So I'm going to do it first.
Okay.
And it would be help perhaps if we dry the wig a little, because all this has to do with humidity. Okay, so Rachel, if you watch carefully, you know what's going to happen, and you know what is not going to happen, okay? I better put my shoes on, because you never know. Okay. So. All right. Marcos, go ahead. Working? You see it? Looks cool, right? Okay, now let me first dry your hair. Why don't you come here? Rachel. Okay. I will ask Marcos again to turn it on because I would love to see this myself. Don't do anything. So stand on here, don't do anything. Discharge? Oh, yeah. Yeah? Okay, now put your hand on there, and no matter what happens, stay where you are. Okay? You're not nervous?
No.
Good.
Just slightly amused.
Good. Okay, Marcos. Oh, you didn't wash your hair this morning. Move your hair a little like this. Ah, there we go. A little more. Yeah. I think it looks. You look better actually than you looked before. Okay. Don't do anything yet. Take your hand off. Okay. Take your hand off. Turn it off. Yeah. Okay, thank you, Rachel. You were terrific. So the time has come now to make the ultimate test and to see whether this Van de Graaff can actually kill me or not. if I stand here and touch the Van de Graaff, and Marcos powers it up, there will be a current going through me, and that would be a test. However, you may say, yeah, sure, they turned something on, but there was no current going through Walter Lewin. So therefore, you deserve proof that actually current is going through me. And just like we did with Alex, the proof will be, if it works at all, that I will have a fluorescent tube. I have it here. And this has a nice insulator on it here. And I will go close to the Van de Graaff. And then I will touch it here, which then, for the Van de Graaff, is the easiest way to have a current from here going through the air first, through the tube, which would make light then, and then through me. Now, the best way to do it, of course, is take my shoes off, because my shoes have a high resistance. And so for me to get the full blast, the real current, would be, of course, without shoes. Now, there's one thing I have to tell you, and that is I have never tried this before. No volunteers, oh no. I've never tried this before, so it is possible that this is my last lecture. In which case, next Monday, tomorrow, no 803 lecture. We need some darkness again.
This was a question.
Oh, there is a question.
Would the fluorescent tube have resistance?
Excuse me?
Fluorescent tube have resistance?
Yes, it does. And that's a very good point. Of course it has. But still, you will see that if I put my hand here, that the easiest way for the dome of the Van de Graaff to discharge is this routing. In other words, this routing will have a lower resistance than any other routing to the floor of the building. That's a very good point. Yes, it does. But you would agree, right? If you see the tube lit up and you see me stand like this, then you know that the current goes through me, right? And you would feel very sorry, I hope. All right, let's go. So, Marcos, are we going to make it very dark?
Yes.
Completely dark. Susan, you think you can handle this?
Yes. Easily.
Okay, turn it on. Touch, 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 touch. I touch it. I touch it. Ah! I touch it. I touch the tube. I touch the tube. No! 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 So, the current went through me, and it didn't kill me. And why did it not kill me? Because the amount of charge on the dome is very little. The current through me may have been high, but it is so short that it is not long enough to kill me. And that's why these instruments are potentially dangerous, but if you handle them well, then it's not so bad. For those of you who are still in high school, or maybe like Rose, not even in high school, I would say come to MIT and tell the admission office that you have a personal invitation from me, where you say that they will not turn you down. And I'll teach you a lot more about electricity and magnetism. Now, your parents may think now that you know it all after this lecture, but believe me, there is just a little bit more to be learned about electricity and magnetism. So maybe I will see some of you in my classes in a few years. And by the way, thanks for coming today, and above all, of course, thank you parents for bringing your kids here. But of course, also thank you to my colleagues who are here, and thank you for my students and my ex-students, and even some graduate students who are here. But thank you, Marcos Henking. Your contributions to all my lectures, not only to this one, but to all my lectures, are invaluable. Thank you, Marcos, and thank you all.